Hi, it's time for another math easy solution. Today we're going to discuss further into differential equations and now look at example 1, part 2 of that example 1 video on predator-prey systems, which I went over in my last video, so make sure to check that out. And in that previous example, I went over A, B, and C of this example, but now in this video, I'm going to go over part D and E. So yeah, make sure to watch that earlier video. Put the link in the description below. But basically, in that video, just to recap, these were the predator-prey equations that we were given. So these two right here, and then part A, find the solution of the constant solution, which were these. Rabbits was 1,000 rabbits and 80 wolves, and then for the trivial one is obviously if you have 0 rabbits and 0 wolves. Then part B was using chain rule to write a derivative in terms of dw and dr, so you remove that time component in the derivative. So these were functions of time, or derivatives in terms of times. This one's a derivative of the wolf in terms of the rabbit. In other words, change in the wolf population with the change in rabbit population. And in part C, we went over the direction field. You can click here as a link to it. For that dw over dr term. So you got something that looks like this. So let's go back here, and now let's look at part D, and then we'll do part E after. So part D states, suppose that at some point in time there are 1,000 rabbits and 40 wolves, and then it states, draw the corresponding solution curve and use it to describe the changes in both population levels. So what we could do is use a direction field to start off at 1,000 rabbits, 40 wolves, and then see where we go from there and how the populations change. So put a line here. And here I've copied and pasted that direction field from part C. So D states, so using the direction field from part C and starting at R equals 1,000 and W equals 40. Well, first I'll just write this. This is W, that axis. In that link there, they don't have, you can't change the variable, so then in our case, the W is, the Y is equal to W. Put an equal sign like that. So Y is referring to W, and T is referring to R, because you can only use Y and T in that, and you can see that here. You can only deal with Y and T, but in our case, R and W. So then the x-axis here is going to be R. And then this 3e to the 3 plus 0, 3, this is saying it's 3,000. It's another way. This one here is 2,700, etc. So that's this exponential notation. And now let's start off at our 1,000 and 40. So 1,000 is roughly here, which is the center point here. Recall is the center point of the constant solution, 80 and 1,000. But in our case, let's say we have 1,000 right here. So we go up all the way here to 40. 40 is somewhere here, 45. So this would be 35, 40, which would be 2/3, somewhere around there, I would think. So moving across this up to here. So this is roughly the point. This could be our P 0, and which is at 1,040, like that. So now the question is, do we go clockwise, do we go to the left, or do we go to the right in this case, from this direction field? So starting at P0 at time equals 0 and letting T increase. So let's say we're starting at time is 0, and as time goes on, do we move clockwise or counterclockwise around the phase trajectory? That's the solution curve which we will draw. And here it says, so basically we can find that out if we put R equals to 1,000 and W equals 40 in the first differential equation. And the first differential equation is, again, if you go to the model, so the model is here, dr over dt equals to 0.08R minus 0.001 RW. And we're doing this because to see if the growth rate of the rabbit is growing or decreasing. So if it's growing, then the rabbits are going to go to the right side or counterclockwise. So if we put 1,000 in there, let's just recall dr over dt is equal to 0.08R, and this was a minus 0.001 RW. I believe that was right. Let's just double check. And that is, yeah, that's correct right there. So, yeah, so in our case, what we have is this R equals 1,000 and W equals 40. So let's just plug that in. So we have dr over dt is equal to 0.08 times it by 1,000. And then this is minus 0.001, rabbit population is 1,000. And then wolf population is 40. Oops. 40, like that. And now we could simplify this further, and we can do that by, well, remove this fraction, this 0.08, the decimal place, try to write it as a fraction. And if you move this to the right, you can move it 1, 2 decimal places. So in other words, we could write this as 8 over 100. It's the same thing as 0.08. Times it by 1,000. And now we subtract it by, this is, we can move this to 3 times the decimal place of 1, 2, and 3, getting a 1 over 1,000. And then we have times it by 1,000 times by 40. So as you can see, this 1,000 cancels with this, and then this cancels with the 2 of these, so then we're left with 10 times 8. In other words, we get an 80 minus, this all cancels, but we are left with the 40. So minus 40, so this equals to 40. Yeah, so now this 40, well, that's obviously greater than 0. So that means that the derivative when the rabbit population is 1,000 and the wolf population is 40, the derivative in terms of the rabbit with time is increasing. It's greater than 0. So since dr over dt is greater than 0, this means that r is increasing at p0, and so we move counterclockwise around the phase trajectory. So in other words, we're going towards wherever the axis is increasing. So we're going to move over to this side like that. And then I'm basically going to describe what we're doing. So I'll put a space here. So we see that at P0, yeah, at P0 equals to, actually, no, I don't know what this is, 0, this is typo there. So we realize we see that at P0 there aren't enough wolves to maintain a balance between the populations, so the rabbit population increases. So that's basically what it means, that the derivative of dr over dt is increasing, so that means that there isn't that many wolves, so then the rabbits can keep increasing, assuming there's a plentiful food, and keeps going like that. The next thing I have, so that results in more wolves, and eventually there'll be so many wolves that the rabbits have a hard time avoiding them. Because again, when you increase rabbits, you're obviously going to increase the amount of wolves because they could eat more rabbits and reproduce. Yeah, so then the rabbits, so number of rabbits begin to decline. And then at P1 where we estimate, and this is at P1 where we estimate that R reaches its maximum population of rabbits of about 2,800. So that's my calculus book writes, and then the way it graphs, it goes all the way roughly up to this 2,800 mark. So it keeps going, you follow along this curve. So basically we're getting increasing in the number of rabbits, and then eventually it just levels off somewhere here, like that. I assume, so this one, let's make this a bit more accurate, so somewhere around there. So then at this point is where the rabbits start to decrease because there's too many wolves. So once we get about around this mark, we're going to have too many wolves there. We're going to have too many, there's going to be a lot of rabbits, but then the number of wolves is increasing, and now the wolves are eating more of the rabbits than they are reproducing. And this one is point P1. We'll write it like that. And then the next step, yeah, so the number of rabbits decline at P1 where we estimate that's at R reaches roughly 2,800. This means that at some later point the wolf population starts to fall, and it's at P2 where R is 1,000 and W is about 140. So and we could see that here when we follow this along, and then it's roughly, if this is 140, 1,000 is somewhere here, and it does look like it's going there as well. So this mark right here, so my calculus book has this as P2, and as you can see, this even follows it along. So at this mark right here, we're seeing that, well, the population is going to start, the wolf population is going to start decreasing because a lot of these rabbits are being eaten. So once the rabbit population decreases, and then the wolf population decreases because there just isn't enough food, and then this follows a path like that as well. Yeah, so let's see the next step in this. And yeah, so then this right here, yeah, this means at some later point wolf population starts to fall. That's at P2, where R is 1,000 and W is about 140. But this benefits the rabbits because if there's less wolves, then the rabbits can reproduce properly again. So the population starts to increase at point P3, where W is about 80 and R is about 210. So let's go over here. Yeah, so my calculus book has it at R is about 80, so let's just say somewhere there. And then this point right here, R80, and then about 210. So somewhere about here is their P3 point. And then this one, as you can see, it's following along the trajectory. You just follow along these slopes of the direction field. And then at this point, the wolf population is decreasing while the rabbit population starts to increase again because there's less and less wolves. Like that keeps going across, and it eventually goes back to the cycle. And then it just repeats the cycle. So there's the phase trajectory. And let's see the notes I have written down to describe this. And again, yeah, this benefits the rabbits, so their population starts to increase at P3, but W is 80, R is at 210. And as a consequence of the wolf population eventually starts to increase as well. This happens when the population return to their values of R equals 1,000 and W equals 40, and then the entire cycle begins again. So yeah, whenever you start increasing the wolf population, you're obviously gonna, increasing the rabbit population, the wolf population increases. As those increase, the rabbit population eventually decreases, and then the cycle keeps repeating, which is pretty cool. Stuff like that. Yeah, so now let's look at part E. So part E says use part D to make sketches of R and W as functions of time. Okay, so let's scroll over here. Yeah, so here I've copied and pasted the graphs of these functions that my calculus book drew, and I'll go over how they went about it. So basically from the description in part D on how, not O, so on how the rabbit and wolf populations rise and fall, we can sketch the graphs of RT and W of T. And basically suppose that the points P1, P2, and P3 are reached at times T1, T2, and T3. So we can look at this graph when we know roughly these values at each of these points, and then we could plot those out assuming a time T1, T2, and T3. So for the R population, right here, then we could sketch graphs of R and W. So for the R and T graph like this, so initially let's say we have, this is at T0, or P0, this is when we have 1,000 rabbits and 40 wolves. So going up here, so 1,000 rabbits, 40 wolves. Then at this point here is roughly about 80 wolves and about, this is about 3,000. My calculus book uses about 280, so this is a bit off scale. So we'll just go about 280-ish. It's close enough. So yeah, so what we do is, so this one's at 1,000, but then for the wolf population at W, we start at 40. And then at T1, it goes up to roughly, at this point right here, remember this wolf population is about 280 or close to 3,000, whichever one you want to use. Yeah, I'll just use 2,800 just because my calculus book uses it. So that's at that point right here, and I'll put the coordinates as T1 and then 280, 2,800 like that. But then over here at T1, you could see that it goes up to 80, because remember the points were 80 and 2,880. So now we have at this point T1 and 80. And then at T2 we have it roughly here, and this one is again, if we scroll up here, this one is at P2, that's about 140 and 1,000 like that. So we get to 1,000 here, so this is about T2 and 1,000. And then, but for the wolf population at T2, we have it close to 140. So this one is at T2 and 140. So it goes from here, it goes from there, it goes to there. And now we look at the last one, T3. And T3 is about 80 wolves and this was about 210 rabbits. Yeah, and that's what my calculus book uses, 210 roughly. So then that's at the very low end here, T3. And this is at 2, yeah, so T3, and then this is at 210. But then for the wolf population, it was at about 80. So at this point here, this is T3 and about 80, like that. So basically you would go up, and then you would go back down, and then finally you get back to this cycle, which was at 40 wolves and 1,000 rabbits. So that's at this point here. And then after this, well, the cycle just repeats. So cycle repeats. And the same thing with the rabbit population as well. You eventually go back to the 1,000 rabbits and 40 wolves. And then after this, the cycle repeats. Cycle repeats over and over again. And again, you would just go up, down, up, down, up, down through time. And then you just have a repetition like that. And now here, so to make the graphs easier to compare, we can draw the graphs on the same axis, but with different scales for R and W. So this is the reddish one or pink one is the wolf population on the right side on the secondary axis, and then the number of rabbits in blue in blue on the left axis, the main axis, like that. And as you can see, they're just separated by almost a quarter of a cycle. So if a full cycle is roughly, this is the 1,000, has to go back to the 1,000 here and here. So this is, after this is when the cycle repeats. So we could say a full cycle is from here to here, from here to here. And as you can see, whenever there's a high rabbit population, and then like about a quarter of a cycle, there's a maximum wolf population, and then everything starts going down. Yeah, and the wolf population drops as the rabbit population drops as well, but then it gets to the point where the rabbit population is really low, that the wolf population drops a lot, and eventually it's going to start growing because there's less wolves. But again, there's always a phase, or like a quarter of a phase different, where you have max rabbits and then followed by max wolves, which makes sense because the food supply for the wolves is the highest, and then eventually you're going to have the highest wolf population, and then it decreases after that. So as stated here, or as I stated earlier, so notice that the rabbits reach their maximum population about a quarter of a cycle before the wolves. And an important part of the modeling process is to interpret our mathematical conclusions as real-world predictions and to test the predictions against real data. So I also have some real data here. So the Hudson's Bay Company, which started trading in animal furs in Canada in 1670, has kept records that date back to the 1840s. And figure 6, that's this figure actually. Yeah, and here just change that, just write the figure below, just because I just copied this from my calculus book. So the figure below shows graphs of the number of pelts, in other words, just furs, of the snowshoe hare and its predator, the Canadian lynx, which is like a wild cat, and the hare is like a rabbit. Anyway, so it's traded by the company over a 90-year period, so about 90 years there. And you could see the coupled oscillations in the hare and lynx populations predicted by the Lotka-Volterra model do actually occur, and the period of these cycles is roughly 10 years. So basically, yeah, this is the data here, and you could see the same kind of graph I have above. So the hare is the blue, that's the prey, and the predator is the lynx. And as you can see, whenever there's a high, and these are in thousands of lynx, this is a lot of fur that they were selling. So here, whenever you had a maximum here, for example, the hare, it's followed by the lynx maximum, and then decreases, and there's always like a shift. So there's always a phase shift away, and then whenever there's the highest hares, and then it's roughly followed by highest lynx, and this one is a bit corresponding towards each other. So this one's high hare and high lynx, but then overall you have a separation like this. Yeah, so this is pretty interesting stuff. So, and generally, it does follow the Lotka-Volterra model that we went over here, where it's always a phase shift like that, and it goes up and down, very, very similarly to this real-world data. And basically, although the relatively simple Lotka-Volterra model that we were using, that's the predator-prey system that I've covered so far, has had some success in explaining and predicting coupled populations, more sophisticated models have also been proposed. One way to modify the Lotka-Volterra equations is to assume that in the absence of predators, the prey grow according to a logistic model with a carrying capacity, K. So instead of using just that simple model, you could couple it with the logistic model that I've covered also in my earlier videos. Then the Lotka-Volterra equations are replaced by the system of differential equations, something that looks like this. So for the rabbit one, so this is the prey can grow relative to this. So dr over dt is equal to kr, and then multiply this by the 1 minus r over capital K, which is the carrying capacity. So if there was no wolves, it would grow, and then would grow exponentially, and then add a limiting factor of the K, and then again minus the ARW, or the presence of the wolves or the predator, and then coupled with the one we've already covered, dW over dt, which equals to, well, just it's the decreasing population minus RW, but it's increasing with contact with the rabbits by this term, B times R and then W, like that. And also what's interesting is models have also been proposed to describe and predict population levels of two species that compete for the same resources or cooperate for mutual benefit, as opposed to a simple predator-prey system. And I may cover examples on these models in later examples, so stay tuned for those videos. Anyways, that's all for today. Hopefully you'll learn from this pretty extensive example, and also showing some real-world data that aligns pretty generally well with these models that I've covered right here. Anyways, that's all for today. Hopefully you'll learn, and like always, you can download these exact notes in the link below. Thanks for watching, and stay tuned for another Math Easy solution.